Hi everybody. I'd like to go over how to balance oxidation reduction or redox reactions by way of example using the half reaction method. Here's an example of a reaction that's occurring in basic solution, or a solution that contains a lot of OH ions or hydroxide ions. Well, when we're using the half reaction method, we need to break up this reaction into two half reactions, an oxidation half and a reduction half. So in order to do that, we first have to identify what chemical species is being oxidized and what is being reduced. So below I've looked at silver and checked out silver on both sides to see if its oxidation number increases. And sure enough, it does. Silver goes from a free state, so that means 0 oxidation number, to a +1 oxidation number. Now the reason I can tell that is because if I look over on the product side, the reason I can tell it's a +1 on the right is because we have two cyanide ions now, polyatomic ions. Each cyanide ion has a negative charge a -1 charge. So if we have two of those at -1 apiece, that adds up to a total of -2. Now the total charge for this whole complex here is -1. So that must mean that silver must be a +1. So that when we add a +1 and a -2, it comes out to be -1, which is exactly what the overall charge is. So silver's oxidation number on the product side is a +1. On the left-hand side, it's a 0. The oxidation number increased, therefore silver is being oxidized. It's undergoing oxidation. So that must mean that either the cyanide ion or the oxygen is being reduced. We'll check out the cyanide. We see that we have cyanide on the left, carbon with a +4, nitrogen with a -5, oxidation number adding up to a total of -1. And here we have two cyanide ions on the right, each one still maintaining its -1 charge, for a total of -1 and -1 equals -2. Silver has a +1. +1 and a -2 adds up to a total charge of -1. So we still see that the carbon's oxidation number is +4 on the left and +4 on the right. Nitrogen's is -5 on the left and -5 on the right. Now, since the silver element is increasing in oxidation number, it is the one being oxidized. The carbon and nitrogen's oxidation numbers are not changing, so therefore it must be that the oxygen is being reduced. So I just wrote down the oxidation half reaction, and I included the cyanide here just because it's part of the product. Okay, so this is an unbalanced oxidation half reaction. Okay, again, remember I said that since this is the oxidation half, that must mean that the oxygen is undergoing reduction. So it's the oxygen that's being reduced. So therefore, we'll write oxygen as a reactant produces something. So this is an incomplete reduction half reaction. Now, you might recall from class that when balancing oxygens and hydrogens, requires adding H2O to the side that needs oxygen, and then following up with putting H pluses at the other side. So, what do? Well, what if I add two H2Os to the right? I add 2 because that gives us 2 oxygens on the right, which balances out our 2 oxygens on the left. Okay, but in the process of adding the oxygens on the right, I also added 2 times 2, or 4 hydrogens. So that must mean that I need to put some hydrogens, H pluses, on the left-hand side, on the reactant side of this half reaction. See? So now our elements, our O's and H's, are all balanced in the reduction half reaction. Now let's finish balancing both half reactions. You might recall that when you have your half reactions laid out, you want to balance all of the elements other than oxygen and hydrogen first, and then add water and H pluses to balance out your oxygens and hydrogens. Okay? And then check your charges. And if the charges are unbalanced, we'll add electrons to one side or another so that we can balance out the charges. Okay, that's at least the major part of the balancing act. So we have our oxidation half reaction right here, as written before. I just wrote it again so you can see it easily. It's not balanced. And then we have our reduction half reaction with the water added to the right hand side and the 2 waters and the 4 H pluses added to the left. Okay, so what's the next step? Well, what we need to do is balance the charge. So let's take a look at our oxidation half first and take care of business there. Okay, we see that we have a -1 charge on the left, and we have a -1 charge on the right. Okay, but I think before we do that, I made a mistake. What we have to do is make sure we balance the elements first before we mess with our charges. So I'm sorry, I hope I didn't confuse you there. So let's first take a look. We have 2 CNs on the right and only 1 CN, or 1 cyanide, on the left. So let's go ahead then and put a 2 in front of the cyanide on the left here. And now we have 2 CNs on the left, 2 CNs on the right. So that's good. We're pretty well balanced right there. Okay. So now what? Well, we can take a look and look at our charges. Okay, now we have 2 negatives on the left, right? It's a -2 over here, and there's only a -1 on the right. Remember, the charges have to balance as well as the elements. So in order to do that, the only thing we are allowed to add are electrons. It's -2 on the left, total of -1 so far on the right. So if we add 1 more electron on the right hand side, electron, remember, has a charge of -1, that's going to add another -1 on the right and give us a -2, just like we have on the left. So we have 1 silver, 2 cyanides yield silver cyanide and an electron. Now let's look at our reduction half. Okay, we already balanced the elements from before in adding the water and the H plus. Now let's check our charges. Over on the left side, we have what? We have +4. And over on the right hand side, the total charge is neutral, it's 0. So what we're going to need to do is add how many electrons? 4 electrons to the left hand side at -1 apiece. Those 4 electrons then cancels out the 4 positives here. It ends up with 0 charge on the left, which is exactly the same as 0 charge on the right. So now we have the charges balanced. Now problem is, if we want to add the two half reactions together to get a whole reaction, it's not going to work out real well yet, because we have an unequal number of electrons in the oxidation half and the reduction half. If you recall, oxidation reduction means the oxidation half gives its electrons to the reduction half. And here, it doesn't look so good, does it? What we need to do then is we need to multiply the oxidation half reaction by how much in order to get the same number of electrons? Well, 4. We have 4 electrons in the reduction half reaction, and so we need to have 4 here. Sometimes, when you have unequal number of electrons, you have to actually multiply each one of these by some different number in order to reach a common multiple. But in this case, all we have to do is multiply that first reaction by 4. So let's do that. So I have to multiply each term by 4. So I'm going to take 4 times 1 is 4 here. 4 times 2 gives us 8. 4 times 1 gives us 4. And 4 times 1 gives us 4. So it's 4, 8, 4, 4. Okay? Alright, so now we can see then that we have 4 electrons given away by the oxidation half, and those 4 electrons then are going to be grabbed by the oxidation half of the reaction. Okay, next step. So now that the elements and charges are balanced, we can make sure each half shows the same number of electrons and then add the two half reactions together. We saw that from before. We had 4 silvers, 8 cyanides produce 4 silver cyanides and 4 electrons. The oxidation half, we have this. Now let's add the two half reactions together and see what we get. Okay, so we have 4 silvers, I'll write that down, plus 8 cyanides, plus 1 O2, plus 4 H pluses, plus 4 electrons, produce, or equal if you want to call it that, 4 silver cyanides, plus 4 electrons, plus 2 H2O. Now let's try to simplify as much as possible. Okay, well, I see that we can subtract 4 electrons from each side. So that gets rid of our 4 electrons. And that makes sense too, because the oxidation half is giving its 4 electrons over to the reduction half. So they kind of get hidden in the process, right? They're used. Now, if we could separate those two half reactions in 2 separate test tubes, for example, and then run a wire from one test tube to the other, we could actually reroute the electrons and have the oxidation half give its 4 electrons through the external circuit wire, maybe through a light bulb or a motor, and then be pulled into the reduction half of the other test tube. And that would drive current through an external circuit and actually do some useful work. Okay, so far so good. We've gotten rid of our electrons, basically subtract 4 electrons from each side. And what about anything else? Can we simplify? Well, we have, well, let's not, I don't see anything that can be combined to simplify it at this point. So that looks pretty good so far. Now remember, I said that this is in a basic solution. And basic means OH. I don't see any OHs here. All I see is a lot of H pluses, which would indicate that this is in an acidic solution. This would be our end answer if the original question asked you to balance it as if it were in acidic solution. But since it's in basic solution, we have one more step. Okay, so since it's in the basic solution, we need to add OH ions to both sides in order to eliminate the H pluses. Okay, so how do we do that? Well, if I add 4 OHs to the left side and to the right side, because remember, if you add something to one side of an equation, you must also add that same value to the other side in order to keep it as an equation. What happens here? Well, OHs added to H pluses give you H2O. So we end up with 4 H2Os here, and these basically just then are used up to form those 4 H2Os. Okay, so now we have 4Ag plus 8Cn minus plus O2 plus 4H2O yields 4Ag cyanides plus 2 H2Os plus 4 OHs. Those 4 OHs are going to remain in the solution, and that's what makes this solution basic. The last step, though, is to simplify this. It's not simplified enough because you see here we have 2 H2Os right here and 4 H2Os on the left. So we better combine like terms, simplify this problem out. So that means I'm going to subtract 2 H2Os from both sides. That'll get all our H2Os on the other side. So we end up with 2 H2Os for 4 H2Os is 2 H2Os on the left, no H2Os anymore on the right. We still have our 4Ag plus 8Cn minus plus O2 with the 2 H2O, and that gives 4Ag Cn plus 4 OH minus. And so this, my friends, is the balanced redox reaction. Thank you very much, everybody.